You know, earthquakes, they feel like the definition of chaos, right? Just these totally unpredictable, destructive forces. But what if I told you that underneath all that randomness, there's actually a secret geometric pattern? Well, today we're going to dive into a really fascinating scientific paper that found exactly that, a kind of hidden mathematical order in the middle of all that seismic chaos.
So the big question is, how can something as wild as an earthquake possibly follow any kind of rule book? It seems impossible. But the researchers behind this paper, they found the answer. And it's not in the stuff we learned in high school geometry, perfect circles and straight lines. Nope, it's in the jagged, branching, messy patterns that you see all over nature. Think about lightning bolts, or snowflakes, or even the shape of a coastline.
Okay, so to really get what this paper is talking about, we've got to wrap our heads around the main idea, and that is fractal geometry. It's a whole different way of looking at the world, one that goes way beyond the simple shapes we're used to.
So what exactly is a fractal? The best way to think about it is to picture a coastline. You know how from a satellite it looks all jagged and complicated? Well, if you zoom in on just one little part of it, that part is also jagged and complicated. And if you zoom in on a single rock on that beach, its surface is jagged too. That's the key idea, a pattern that repeats itself no matter how close you look. We call that self-similarity. And because it's so complex, you can't describe it with simple dimensions like 1D, 2D, or 3D. It actually lives in between them in what we call a fractional dimension. Kind of weird, right?
And this right here really lays out the two different ways of seeing the world. On one side, you've got your classic Euclidean geometry, the stuff from school. It's all about smooth, predictable shapes, lines, squares, cubes, simple whole dimensions. But then, on the other side, you've got the fractal geometry of the real world. It's rough, it's complex, and it hangs out in those weird in-between dimensions. And that's what makes it so perfect for describing things like clouds and coastlines, and, as we're about to see, the very ground we stand on. Okay, so a cloud or a coastline being fractal, that kind of makes sense. You can see the pattern. But what in the world does this have to do with earthquakes? Well, it turns out the connection is way more direct than you might think.
Here's the core argument from the paper. Earthquakes don't happen in some smooth, perfect textbook world. No, they happen deep inside the Earth's crust, which is this incredibly messy, fractured, and super complex environment. And that environment, it is fundamentally fractal.
And this is exactly what we mean when we say that. The study points to all these geological features, things like fractured rock surfaces, and of course, the fault zones where earthquakes are born. These things aren't just simple, straight lines or flat planes. Not at all. They're these intricate, branching, self-similar patterns. I mean, they're textbook fractals.
All right, so if earthquakes are happening in a fractal world, what does that actually do to the seismic waves they create, right? That's the million-dollar question, and it's exactly what these researchers wanted to find out. Now, to figure this out, they couldn't just use the old playbook. See, the standard physics equations, they all assume waves are traveling through a nice, smooth, uniform space. But we know the Earth's crust isn't like that. It's fractal. So they had to invent a brand new tool, a new seismic wave equation that could actually model what a wave does when it's forced to travel through a complex, jagged path.
Okay, let's start with a baseline. This is what a seismic wave is supposed to look like in a conventional model. See? A perfect, regular, repeating wave. In this simulation, the fractal dimension, which they call alpha, is set to 1. That basically means it's a simple, straight, non-fractal line. Super clean, totally predictable. But now, watch what happens when we start making that path just a little bit more complex, a little more jagged. Here, they set the fractal dimension, alpha, to 0.75. And boom, the wave immediately starts to change. It's not that perfect repeating pattern anymore. The peaks start to get wider, and the whole shape just begins to warp.
Okay, let's push it even further. Now alpha is down to 0.5, which means the medium it's traveling through is way more fragmented. And just look at that wave. It's seriously distorted now. That nice clean pattern from the beginning, it's basically gone, replaced by this one big stretched out pulse.
And finally, here we are at an alpha of 0.25. This represents a really, really complex and fragmented path. And, well, the wave's classic shape is just gone. The oscillation has almost completely flatlined. It's like the fractal geometry of its environment has totally smothered the wave's movement.
So, okay, the shape of the wave gets totally messed up. That's pretty cool to see. But this visual change was just the tip of the iceberg. It actually led the researchers to a discovery that was way more profound. Something that could completely change how we think about the real power of an earthquake. It turns out, depending on the exact conditions, the model shows the wave can go one of two ways. On the left, it can become what's called a deformed plane wave. It's still moving forward, but its shape is all warped. Or, as you see on the right, it can become a decaying wave, where it basically just fizzles out and fades away the further it goes. But honestly, the shape of the wave, that was only half the story. The really shocking discovery, the one that made everyone sit up and take notice, wasn't about the shape at all. It was about the energy these waves were carrying. Turns out, the standard models might be missing something huge.
10 times. Let that sink in. 10 times more. What their new model predicted was absolutely stunning. For certain types of slow earthquakes, happening in a medium with a fractal dimension of about 1/2, the total energy released could be 10 times more than what the old models would tell you. It's like these complex fractal pathways aren't just changing the wave's shape, they're acting like a hidden reservoir for energy, allowing way more to be stored and released than anyone thought possible.
And this isn't just some wild interpretation. This is a direct quote right from the paper's abstract. They spell it out in black and white. The energy in their fractal model, which they call E alpha, is about 10 times the conventional energy, EC. It's a game changer. That complex geometry isn't just a fun visual effect. It completely rewrites the energy equation.
So what does this all add up to? Well, this discovery is like getting a brand new pair of glasses. It gives us a completely new way to look at seismology, and it strongly suggests that our whole understanding of earthquake energy might have some major blind spots.
The bottom line is this: by accepting that the Earth's crust is fractal, that it's messy and complex, we can build way more accurate models. This isn't just some abstract math exercise. This could help us get a much better handle on the true amount of energy that gets unleashed during certain quakes, especially those weird, slow-moving ones that have always been a real puzzle for scientists.
And that really leaves us with one last mind-bending question. If looking at the world through a fractal lens can uncover a hidden truth about something as huge and powerful as an earthquake, where else are these secrets hiding? Think about it. From the way our own blood vessels branch out to the crazy ups and downs of the stock market, what other parts of our world are just waiting for us to see them through the right geometric lens? What else are we missing?